All right, so I'm just going to run through our Unit 1, Day 2 notes. Just to refresh your memory, day 1, we learned what terms are, and I just kind of put that little reminder right here. So remember, in an expression, because that's all we've done so far, an expression is just a collection of terms, and terms are separated by plus and minus signs, right? And so now we're going to talk about how to simplify expressions even more than yesterday. So yesterday we talked about simplifying expressions by using the order of operations, or PEMDAS, right, in order to do our math problems correctly. But when we're using PEMDAS, a lot of times on those questions yesterday, all those questions just had numbers in them, and it was all numbers, and there were no variables. So today we're going to talk about how to simplify expressions that have variables in them as well, and not just numbers to calculate using PEMDAS, okay? So the first thing we're going to talk about is like terms. Like terms are super important because if we see two things that are alike, that means we can combine them together. For example, if I had a group of 3 dogs, let's say, and then I looked to my left and I saw another group of 4 dogs, I would easily be able to group them together and make a group of 7 dogs, right? Because I had 3 on my right and 4 on my left, so we may as well just group them all together because they are alike. Right? And so we can do that in math as well, right? So anything that we see that is alike, we want to combine because we want to make our expressions as little as possible because we don't want to sit there and stare at like a 10-term expression. If we are able to actually condense it and make it smaller, it's much easier for us to work with. Okay, so that's what we're going to be doing today, right? We're going to be taking big expressions and we're going to simplify them down as much as we possibly can. And one of the things that we look for is like terms. So as far as definitions go, right, the definition of like terms is like terms must have the same variable. I'm actually going to put variables, right, in parentheses, because obviously a term can have more than one variable if it wants to be. But it can't just have the same variable. It also that variable must have the same power or the same exponent. Okay, so I have a chart here of some examples of like terms versus unlike terms, so you can kind of see the difference. So let's look at those like terms just really quickly. Oops. So in the like terms column, we have 2x, which means we have 2 x's, right? 2x means x plus x, basically. So I just have a group of 2 x's sitting right here, but then it looks like I'm adding another group of 6 x's. Well, x's are the same as x's, so that makes them like terms. So when we add them together, we get 8 total x's, right? And that would be a much simpler expression than the one we started with because we went from 2 terms down to just 1 term, which is a good thing. Okay. The second one underneath that, we're not talking about x's anymore. Now we're talking about m squareds, right? And again, I don't really care about the square. I just know that m squareds can only be combined with other m squareds, right? And it has to be an m squared. I can't combine it with an m cubed or just a plain old m. It has to be an m squared. So if I have 4 m squareds and I take away or subtract 9 m squareds, well, that's going to leave me with negative 5 m squareds. Right, and again, you're just doing the addition or subtraction, right? 4 minus 9 is negative 5, right? You can use your calculator if you need some support with your integers. And then last but not least, we have AB plus 5AB. Please remember that every variable has a number in front of it, has a coefficient like this 5, but we don't always see it, right? So it's important for us to realize that when you see AB right here, there's an understood 1 in front of that AB, right? So when they say AB, they're telling you that you have 1 AB, and we're adding 5 more ABs, which gives us a total of 6 ABs. Right, and so this left-hand side, these were all like terms that we were able to combine and then therefore shrink our expression. Now, if we go to the opposite side, we have unlike terms, right? So if I asked you to simplify the expression 2x plus 6y, you would just be like, well, Miss Juster, that is my answer, right? Because I can't do anything to that because I cannot add x's and y's, right? So we would just leave our answer as this 2-term expression, and you're done. Same thing on the second one. I have p cubes and I have p squareds. Now, obviously, they both have p's in them, but they're not technically the same term. I can only add p cubes to other p cubes, and I don't have any of those. So again, this would be my final answer, and I would not be able to do anything with that. And the same thing applies to our last one. We have this understood 1 again, of course. We have 1xy, but then this is an xyz term, right? And those are not the same, right? An xyz term can only be added to another xyz term. It has to be perfectly identical. And since these are not perfectly identical terms, that means that they cannot be combined. Okay, and when I use the word combine, I'm talking about addition, right? And subtraction, of course, right? So when we want to add and subtract things in math, they have to be the exact same type of term, okay? Now, the cool thing about math is we can multiply anything we want, right? Like if I want to multiply a 5 times a z, it's cool. I just mash it together and say 5z, right? So in math, you can multiply whatever you please, but you can only add and subtract them if they are alike, right? If they are like terms. All right, so here we're going to practice creating some like terms really quick. So let's look at 15x squared. So I just want you to think to yourself, what would be a term that would be like 15x squared? Well, the 15 part doesn't matter. The x squared is what I'm looking at. So I would need another x squared term. So I'm just going to make one up. How about 3? How about 3x squared? These would be like terms, right? Because, oops, sorry about that. Because they are both x squared terms. And if I wanted to, I could totally add them together because they are like terms, which would give me 18x squareds. All right, so again, as long as they are like terms, we can combine them. All right, just doing that a few more times really quick. So I have an xy cubed term. Again, it has an understood 1 in the front of it. If you don't see a coefficient, it's always an understood 1. So I can only combine xy cubes with other xy cubes. So I'm just going to make up another xy cubed term. How about 4? xy cubed, and because those are like terms, I would be able to add them together, and that would give me a total of 5 xy cubes. Okay, so again, just practicing those like terms. Number 3 over here, notice what kind of term this is. This is a constant. I just want to remind you of that. We learned that vocabulary yesterday. So if you see a constant, well, constants can only be combined with other constants. So I know that if I want to add that -6 to anything, it's going to have to be just a plain old number. So I'm just going to pick 9, let's say, right? And so I can obviously combine those together, which is going to give me 3, right? So constants can only combine with other constants. And then last but not least, we have a -3x. That's an x term, which can only be added or subtracted to another x term. Just to change things up a little bit, I'm going to, instead of adding, I'm going to subtract. That's fine too. That's still technically combining because subtraction just means you're adding a negative, right? So a -3x and a -5x, I can totally combine those, and that would give me a -8x. Again, please remember your integer rules, right? If your integers have the same sign, then you add and keep the sign. If they have opposite signs, then you subtract and take the sign of the larger number, right? And if you still find yourself confusing your integer rules, again, please just use your calculator, right? Just type in -3 minus 5, and it'll tell you that that's -8. All right, so now what we're going to do is we are going to look at these super long expressions. Like, look at this guy, right? He's 6 terms. That's a lot of terms, right? And we typically don't want our expressions to be that long unless absolutely necessary. So I want to see if I can condense that expression or simplify it and merge any like terms together. So the first thing I'm going to do is I'm going to go look at my first term, which is a 6x. And it is a positive 6x because there's not a negative in front of him. And I want to ask myself if there's any other x terms that I can combine him with. And yes, I see an x term right here. And not only is that a 3x, but please remember that it is a -3x, right? Signs always belong to the term behind them, right? So you have to make sure that you keep those signs with their numbers. So we have 6x's minus 3x's, which is going to leave us with 3x's. right? So we combined all those. Then I'm just going to kind of go in order. The order doesn't really matter to me. I'll talk more about that in a second. Next up, I have a constant. So I'm going to scan all the way to the end, and oop, looks like we've got another constant right there. So I'm going to be able to combine my positive 5 with my negative 9, which is going to give me negative 4. And then I'm going to move to my last term, which is a y term. And I notice right next door, I have another y term to him. So I have negative 4y's plus 8y's. So I'm going to do my integers, negative 4 plus 8, which is going to give me positive 4y. And that would be my new simplified expression. So instead of looking at my 6 terms, I condensed it down to 3. Right? Which is always better. Now, I am going to add one little thing. I'm just going to put or right here. At this point in the year, I do not care what order your terms are in. If you maybe did your, maybe you work from like back to front and you did your constants first, let's say, then that means your negative 4 would be in the front. And then maybe you did your y's and then maybe you did your x's. I don't know. And it doesn't matter to me, right? As long as the 4 is negative at all times and the 4y is positive at all times and your 3x term is positive also, I don't care what order you put the terms in, as long as they're all there and they all have the correct positive or negative sign attached to them. Okay, so when you're checking your answers on an answer key, for example, maybe you put yours in a different order than mine and it doesn't make it wrong, right? So I just want to make you aware of that. All right, if you want to, you can pause the video and try the next one on your own and then unpause it to see if you did it right, or you can just keep listening. So I'm going to do this next one exactly like I did the previous one. So I'm just going to start at the front, and it looks like I have a negative 12y. So I'm going to scan the rest of my problem, and looks like I have another y term. And again, I want to remember there's an understood 1 right there in front of that negative y. So it's negative 1y. So I'm going to combine my negative 12y's with my negative 1y, which gives me negative 13y. Okay, then I'm going to go to my next term, which is my x's. And what I happen to notice is I don't have any other x terms anywhere in the problem. And that's okay. Sometimes the terms don't have any like term buddies to combine with. So I am just going to bring that over into my answer. All right, I still need him there. And then I happen to notice that all the terms that are left are all constants. So I have 3 of those guys, right? And there's they don't just have to come in pairs, right? That like we've seen. You can also have 3 of the same term, or 4 or 5. So in this case, we have 3 constants. So you can either put all that in your calculator, or you can just do it in your head. So negative 3 minus 7, right? That's going to give me negative 10. And then negative 10 plus 4 is going to give me negative 6, right? So we're just combining all of those constants. And then this would be my final expression. And again, the order doesn't matter as long as you have all the correct signs. As long as your x is still positive, your 6 is still negative, and your 13y's are still negative, then we're all good. All right, so moving on to the distributive property. All right, now I just want to have a quick conversation with you really fast. I'll just do it up here. I hope you remember from day 1 that there's a difference between PEMDAS parentheses and multiplier parentheses. So for example, 2 plus 3 times, I'm just going to make some small little numbers here, 4 plus 1. If I saw this math problem and because remember, you cannot work a math problem that has parentheses in it, right? Until you've done something to get rid of the parentheses, right? So we always, because parentheses are like math prison, right? We cannot touch any of the numbers inside until the parentheses go away. Now, in this case, this looks like a question like we did yesterday, right? The first thing I notice is like, hey, these are PEMDAS parentheses because I can actually simplify what's inside, right? And so if I were to simplify what's inside, I would get 5. Now I'm going to leave that in parentheses because I still have a 3 in front of that. But now these parentheses, Those are not PEMDAS parentheses anymore because I can't simplify 5 anymore, right? But those are now multiplier parentheses, right? So there's a difference between parentheses that are PEMDAS that I can actually simplify and then parentheses that are showing multiplication, right? And so, of course, then we would apply our PEMDAS rules. Oops. We would do the multiplication first and then add the 2 at the end, and we would get 17, right? So if you're lucky, you'll have stuff inside the parentheses that you can simplify. But, so I'm gonna put a little smiley face over here. That's an easy problem for us to do. But what if my problem, I'm gonna rewrite the exact same problem, except what if my parentheses were x plus 1 instead of 4 plus 1? Well, now I'm kind of in a jam because these are not PEMDAS parentheses anymore because I can't simplify x plus 1 because they're not like terms like we were just talking about up here on this previous page, right? X's can only be combined with other X's and so on. So I'm kind of in trouble because on this side, I was able to use PEMDAS to get rid of my parentheses, but over here, that's not going to be an option. So what do? Well, distributive property to the rescue, right? The distributive property tells us that if you have a pair of parentheses, you will always have a number multiplier in front of the parentheses. And if you don't see one, then it's an understood 1, right? But every parentheses will have a number directly attached to it showing multiplication. So if I can't use PEMDAS to get rid of the parentheses, then I'm going to use the distributive property to get rid of the parentheses, which means everybody inside my parentheses needs to get multiplied by the number on the outside, right? So we're going to multiply. This is a very tiny arrow, right? So we're going to multiply A times B, which gives us AB, and then A times C, which gives us plus AC. And notice the parentheses are gone, which is super amazing. That's totally what we wanted to happen, right? So I'm just going to kind of go back up here just really quick so you can see how this would work in reality. All right, so if I saw this problem, I'm like, oh, crud, I can't do anything with x plus 1. So the only way I'm going to be able to get rid of these parentheses is to take that 3 multiplier and multiply everybody inside the parentheses by that 3. So 3 times x gives me 3x because we just shove it together. And then 3 times 1 is positive 3. And then I can just bring down that 2 hanging on the outside. And I'm like, ooh, hey, I've got some like terms with the constants. So that's going to give me 3x plus 5. And that would be my answer. Okay, so that's how we handle it when we have parentheses that we can't simplify, but we still need to get rid of them somehow, right? That's why we have the distributive property. Now, there is a question on your homework, so I'm going to kind of do an example of right here in this little space. Okay, so we're going to do a math problem really quick, and we're going to simplify it using PEMDAS on the left, and then we're going to simplify it using the distributive property on the right. Took me a lot. All right, so I'm just going to make up a math problem really quick, very similar to the one that we just did a second ago. Actually, I'm just going to use that same problem if that's cool with you, that 2 plus 3 times 4 plus 1, since we already did it with PEMDAS. So, right, this is the exact same problem I just did right here. So we know in PEMDAS, we would simplify the parentheses, which would give us 5. And then we have to multiply before we add. And again, we already talked about all this. So we get a final answer of 17. So that would be simplifying using PEMDAS. But what if I didn't want to use PEMDAS? What if I wanted to use the distributive property anyway, even though I could have used PEMDAS? So I'm going to rewrite the exact same problem. And what I happen to notice is that I have this 3 multiplier that's attached to that parenthesis, which technically means at the end of the day, everybody inside of that parenthesis is going to be multiplied by 3. So if again, the 2 is just going to come down. This 2 has nothing to do with the parentheses, so I'm just going to bring him down. And then I'm going to multiply 3 times 4, which gives me 12. And then I'm going to multiply 3 times that positive 1, which gives me positive 3. And you'll notice at this step, the parentheses have disappeared and we're just left with a basic addition problem. So 2 plus 12 is 14 plus 3. What do you know? I get 17, right? The exact same answer I got with PEMDAS, but in a totally different manner, right? So there is a question on your homework that asks you to compare and contrast the PEMDAS way of simplifying versus the distributive property way of simplifying. So just leaving that there for you in case you need to come back and reference that for your homework assignment, okay? All right, so right now we're really just gonna do a ton of practice problems. I'm gonna go ahead and do this example problem that's sitting right here. So clearly I cannot do anything with x minus 2 because they're not like terms, but I do have this lovely 5 multiplier that's hanging out in front, which is telling me to multiply everybody by 5. So if I multiply x times 5, that gives me 5x, and 5 times negative 2, because that is a negative 2, is going to give me negative 10. And that's it. That's my answer because those are not like terms. I can't combine them, but I did get rid of the parentheses, which again is our ultimate goal today, right? We always want to try to get rid of parentheses because we can't really progress in a math problem that has parentheses in it. All right, so I'm just going to run through these 7 examples really quick. So feel free to pause or rewind or whatever you'd like to do. All right, so obviously on the first one, we are distributing a negative 3. So negative 3 times x is negative 3x. You just shove it together. And then negative 3 times positive 1 is negative 3. Right? And that would be our final answer because I can't combine those because one's an x term and one's a constant. So voila, we are done. Really quick, something I don't want to see. I'm going to erase that really fast. Please try not to do this. Please do not do, okay, negative 3x. Please don't just automatically bring down, that looks really sloppy. Please don't just automatically bring down the plus sign and then say negative 3 times 1 is negative 3, because then you end up with this double signage going on right here. And that is something I do not want to see, right? We never want to have double signs back to back because that's not actually simplified. So please make sure when you're working your problems that you don't write down a positive or negative until you know if your term is positive or negative, right? So negative 3x is negative 3x. And negative 3 times positive 1 is negative 3. So we just want to write minus 3. We don't want to write plus negative 3. All right, and if you do write that, then you need to clean that up and finish the problem. All right, on number 2, remember every parenthesis has a number in front of it. And if you don't see a number, that's because it's an understood 1. And in this case, it's an understood negative 1. So negative 1 times x is negative 1x. And negative 1 times negative 4 is positive 4, because a negative times a negative is a positive. And that's your answer. All right, again, our goal today is to get rid of parentheses. All right, number 3, don't freak out when you see fractions, right? You have a calculator that you can use, so no big deal. Notice I have 3 terms inside, but none of them are like terms. I've got an x term, a z term, and a constant, but I do want to get rid of those darn parentheses, so I'm going to take that 1/2 multiplier, and I'm going to multiply everybody by a half. And if you need to use your calculator, that's great. So 1/2 times 2x, that's going to give me 1x. And you can either write 1x or you can just write the x because the 1 is understood to be in front of it anyway. So if you want to write the 1, have at it, right? It's perfectly fine. Then I'm taking half of 6z, which would give me 3z's. And then I want half of negative 4, which would give me negative 2. And I didn't have any like terms before, and I certainly don't have any like terms now, so that would be our final answer. Okay, this last one, before we step it up a notch, we are multiplying by 2x. All right, so here we go, 2x times 4y. I know there's a lot of variables going on here, but don't let that freak you out. Remember, in math, you can multiply anything you want. You just shove it all together. So 2 times 4 is 8, and x times y is just xy. All right, so just push it all together, and there you go. And then we're going to multiply 2x times negative 3z. So negative 6, because the 2 times negative 3, and then xz. And those are not like terms because xy's are not the same thing as xz's. So that is our final answer. All right, moving on to number 5. Now, the first thing that should jump out at you about number 5 is that you have 2 sets of parentheses. And if I have 2 sets of parentheses, that means I have to do distributive property 2 times, right? So we've got to get rid of this first set of parentheses by distributing the 7 and multiplying the 7 times everybody. Remember, this is a multiplication problem. So 7 times x is 7x. And 7 times positive 4 is positive 28. But then I have a second set of parentheses, and the number in front of him, please be super, super careful here. This is not just a 6 that we're distributing. This is a -6. Remember, plus and minus signs belong to the term behind them, right? So that's not just a 6, it's a -6. Let me draw a better oval. And so we are distributing -6 to the 3 and the minus y. So -6 times 3 is -18, and -6 times -y is positive 6y, because a negative times a negative is a positive. Now, chances are when you've distributed twice, you probably will have some like terms that you need to combine. So that's on you to double check to see if you have any. So I'm going to put a little question here. Like terms. All right, that's always the question you need to ask yourself, right? When you get rid of all the parentheses, do I have any like terms that I can combine? And in this case, yes, I do, because I have a constant here and I have a constant here. So I can go ahead, I'm going to bring down the 7x because I don't have any other x's. I'm going to go ahead and combine 28 minus 18, which is going to give me 10. And then I'm going to bring down that 6y because he doesn't have any y buddies to combine with. And that is going to be our final answer. So all of these homework problems are at most 2 steps, right? Distribute to get rid of parentheses, combine like terms if you have any. Okay? All right, let's hop over here. Again, I know a lot of people freak out when they see fractions. Please don't. These are very friendly fractions. You can either do them in your head or you can also just type them in your calculator. It's not that big of a deal. So clearly to get rid of this parenthesis, we are going to multiply by this positive 4. So I want to multiply positive 4 times 3/4 x. And if you need to, here, I'll just show you a quick example. All right. Let me clear that because I already did it before. If I want to do 4 times 3/4, again, you can type your fraction in. You can just do 3 divided by 4, or you can do your alpha y equals, like we talked about in class, so that it looks just like our paper, right? So if I want to multiply 4 times 3/4, well, that's just going to give me 3, right? So you always have your calculator available to you when you need it. So that's going to give me 3x. And then I need to multiply 4 times 2, which is going to give me 8. And then, of course, I have this parenthesis that I need to get rid of. So I'm going to take this positive 5, and I'm going to distribute him. Well, now I need to multiply 5 times 4/5. So again, if you struggle with that, 5 times alpha y equals enter. So I can type in my little vertical fraction. And 4 it is, right? So I'm going to go back here. So this is going to give me plus 4x. And then positive 5 times -1, which is going to give me -5. And then, of course, we want to ask ourselves, are there any like terms? Question mark. And yes, there are, right? Looks like we've got some 3x's here and some 4x's here. So it looks like we have 7 total x's. And then we've got some constants. We've got a positive 8 and a -5, which is going to end up giving us just 3 when we combine them. And that is our final answer. So we went from that big gross expression to just 7x plus 3, which looks so much nicer, right? We haven't actually changed anything. All of these expressions are equivalent to one another, right? We're just shrinking them down to make them a little friendlier, okay? All right, one more of these. We're almost there. All right, so we definitely have a parentheses that we need to get rid of. So we need to ask ourselves, what is the multiplier in front of the parentheses? And the answer is not -4, right? This -4, he is not directly attached to that parenthesis. He's just a constant. He's just kind of hanging out in the front. So I'm actually just going to bring him down to my next line because he has nothing to do with the parenthesis. The number that's actually attached to the parenthesis, you got it, is the understood -1, right? And so it's a -1 that we are distributing. So if we multiply everybody by -1, that's going to give us -2y minus 5. And once we've gotten rid of our parentheses, then of course we're like, hey, are there any like terms? Because that's always a question you need to ask yourself. And I'm hopefully you're saying yes, right? So we have a constant of -4 and a constant of -5, which is going to give us -9 when we combine them because they're both negative. So you add and keep the sign. And then I'm going to bring down my -2y because I don't have any other y terms to combine him with. Right, and that is our final answer. Again, I don't care what order your terms are in. If you want to write your final answer as -2y minus 9, that would be the exact same thing. Okay? All right. Sorry, taking a quick drink of water. Okay, if you turn to the last page, I don't want this, all of this right here. If you read this, it can be very confusing. So I don't want it to be confusing. A polynomial, I'm just going to write this down. This is a fancy word for an expression. Right? We know from yesterday that an expression is just a collection of terms. And guys, that's all a polynomial is. A polynomial is just a collection of terms. It's the exact same thing we've been talking about. It's just a fancier vocabulary word, right? So I don't want you to freak out when you see the word polynomial, right? It's very much Latin, right? Poly meaning many and nomial meaning names or terms. So it really just means many names or many terms. So it's not that big of a deal. We just want to introduce you to this lingo because we'll start using this terminology a lot in later units, okay? The one thing I do want you to know today is that we do have special names for our polynomials or our expressions, depending on how many terms they end up having. So, and you do need to know these words. So the first one is a monomial, mono meaning one. Okay, so it's pretty easy to remember. So for example, 5x squared y, that's only one term because there are no plus or minus signs, right? And so this is one term. So if you end up with an answer that only has one term in it, we would just refer to that as a monomial. Okay, a binomial, bi meaning two, right, just means you end up with an answer that has two terms. Again, these are just fancy vocabulary words for the same things that we've been talking about since yesterday. Okay, so I don't want it to mess you up at all. And then, of course, trinomial, tri meaning three, like a tricycle, right, means you just end up with an expression that has three terms in it, right? So again, these are just fancy vocabulary words pertaining to stuff that we've been talking about already. Okay, so here's what we're going to do on these next three. We're going to simplify these expressions as much as we possibly can, and then we're going to identify whether it's a monomial, a binomial, or a trinomial. Now, if you happen to get an answer that is 4+ terms, right? So if you have 4 or more terms, then we just call it a polynomial. Right? We don't have a special word for it anymore. We don't say like quadnomial and quintinomial and all that kind of stuff. So it's either a monomial, binomial, trinomial, or just polynomial, meaning many. Okay, so just so you know. All right, here we go. Let's go simplify these expressions. No, the first thing I notice is I have no parentheses, which is super awesome. That means I can just go find some like terms. So it looks like I have some 5x's and 3x's, which would give us 8 total x's. And then we have -12 constants and +2 constants. So we can combine those to get -10. And there you go. That would be our simplified expression. And then would that be a monomial, binomial, or trinomial? Well, since it has two terms, right, that is definitely a binomial. Okay. All right, let's go look at number 2. Number 2 definitely has a set of parentheses. Well, we got to get rid of those suckers first, right? You always have to get rid of parentheses first. So I'm going to distribute the 4. So remember, distributing means multiply, right? So 4 times x is 4x, and 4 times 3 is positive 12. Then I'm just going to bring down all the rest of these terms that are just kind of hanging out. And then I want to ask myself if I have any like terms. And it does look like we have a couple, right? We've got 12 and 2. So we do have some constants. But I do notice that there are no other x's to go with x's. Because remember, x's and x squared's not the same thing. All right, so I'm just going to bring down the 4x. 12 and 2, or 12 and negative 2, gives me 10. And then my 2x squared just comes down to also, because I don't have any other x squareds. And so this would be my final answer. Again, you can put those terms in whatever order you want. And again, would that be a monomial, binomial, or a trinomial? Well, I'm counting 3 terms for my final answer. So that would make this a trinomial. All right, lastly, we've got 4x cubes plus 8x cubes minus 3x cubes. Well, that's pretty awesome because they're all x cubes, right? Which means these are all like terms. So we can just add all of those like terms together. So 4 plus 8 gives me 12, but then I'm taking away 3. So that's going to leave me with 9x cubes. And that would be my final simplified answer, which looks like just one term to me. So this would be a monomial. Okay. All right, we have one application problem to do, and then we are all finished with day 2 notes. So this is talking about a rectangular canvas that this lady's painting on, and it's giving you an algebraic expression for the length of the rectangle and the width of the rectangle. So the first thing they want us to do on part A is to draw and label a picture. Okay, well, it's a rectangular canvas, and you can orient this however you'd like. Now, what you want to be careful of when you label it, it says the length is 4x plus 3. Well, you need to keep in mind, of course, that rectangles have 2 lengths, right? They got one on one side and another length on the other side. So I want to make sure I get both of those lengths labeled so I don't forget one of them. I know the length is in parentheses. If you want to put it in parentheses, you can. That's just letting you know where the expression begins and ends because it's inside of a word problem. So I just kind of dropped the parentheses. And then the width is x plus 2, and just like the length, remember rectangles have 2 widths as well, which of course I'm going to go ahead and I would like you to write this down. If you remember from middle school or elementary school, the formula technically for finding the perimeter is 2 lengths, that's an L, plus 2 widths. So there is a formula to calculate the perimeter of the rectangle, which is what we're going to be doing here in just 1 second. So you are more than welcome to use the formula for the perimeter of a rectangle. You don't have to, though, if you don't want to. I'm going to show you an easier way to do that in just a second. So on part B, it says find the perimeter of the canvas. If you want to, totally use that formula, right? Multiply the lengths by 2 and the widths by 2 and add them together, yay, right? But remember, perimeter just means to add up all the sides. Add up all the sides, right? It's the distance around an object, right? Which is why we add up all the sides. So basically what we're doing is we are going to just start somewhere and we're just going to go around the rectangle and we're going to add up all the sides. Now, if you want to, you can write all that down, like perimeter equals 4x plus 3 plus x plus 2 plus 4x plus 3 plus x plus 2. So if you want to write all of that out, you are more than welcome to, but that's a lot of writing. So I'm definitely not requiring you to do that. What I personally like to do is just use my diagram, right? I don't really write all of that out. I just use my diagram and I just kind of highlight or circle all my like terms. So like I know these 4 x's can be combined with all the other x's. So here's 1 x, here's 4 more x's, and here's 1 more x. So I'm just going to go around the picture and just go ahead and do that in my head and add up all the x's. Well, 4 plus 1 plus 4 plus 1, right? Well, that's 10 total x's. right? And then I can go back through and do the same thing with my constants. I'm like, oh, I've got a +3, a +2, a +3, and a +2. And if I add all that up, I get 10. So that would be the expression that represents the perimeter of the art piece. And if you want to get even more fancy, I am going to write feet on the end, since that's the unit of measure that they're using. Right, so this canvas is 10x plus 10 feet. Now that's not super helpful because I don't know what x equals, but we'll get to that eventually. Okay, so today we're just going to practice adding up all the sides. Okay. All right, there you have it. That is Unit 1, Day 2, right? Distributing and combining like terms. All right, let me know if you guys need any help with that.